And to kick the day off, we have a very special speaker. We're really proud to have him here today, and glad that you're here to to take advantage of it. And we're going to do kind of a two-part introduction to Don. So let me begin with his bio. And as co-founder and chief technology officer, Don Schaefer developed Athens Group's oil and gas practice and leads engineers in delivering software services for exploration, production, and pipeline monitoring systems for clients such as BP, Chevron, ExxonMobil, ConocoPhillips, and Shell. He led groups developing and marketing hardware and software products for Motorola, AMD, and Crystal Semiconductor. Schaefer managed a large PC product group producing award-winning audio components for Apple. From the development of low-level software drivers to the selection and monitoring of semiconductor facilities, he's led key products and process efforts. He received a BS from the United States Air Force Academy and an MBA from the University of Denver. Twice treasurer of the IEEE Computer Society Board of Governors, past editor-in-chief and chair of the IEEE Computer Society Press, and an IEEE senior member and Golden Core member. He is an adjunct professor of engineering at the University of Texas at Austin. Schaefer has contributed to 3 books, written more than 20 published articles, and is co-author of Quality Software Project Management, published by Prentice Hall, and is a certified software development professional. His current projects include the development of a multi-volume set of software engineering proven practices for the oil and gas industry, based on more than a decade of extensive engineering work done at the Athens Group. So that's his bio. But then there's another personal side of it, and Leslie can add some of that. So, Leslie?
Thank you very much, Ron. Welcome and good morning. And I just wanted to ask, how many of you have met someone new or made a new friend here at this conference? So let's see a show of hands. Okay, it's a universal truth. I remember on Thursday night, my friend Jim Kennedy talked about the value of friendship, and that's one of the things that this conference is all about, is making friends, making networking, and making new friends. So I want to mention that I have known Jim and I have known Don. I've known everyone in this room. Whoever these guys are, I can't keep them all straight. I'm looking at Jim, talking about Don. Glad my husband's not here. I have known Don and his family for more than 20 years. I think it's about 30. And he has been a good friend, a leader in the community, in the tech community. He's given wonderful presentations for lots of different IEEE groups. And when the organizing committee asked if there were some local people who could give an inspiring talk, I said, Don Schaefer. And I sent him an email and I said, Don, would you be willing to do this? And Don said, sure. That's the value of friendships. You never know how you're going to need a friend, but when you need them, they're there. And so I encourage you to all keep making friends here and enjoy the next 2 days. So with that, I'll turn it over to Don.
Great. Thank you, Leslie. Thank you. So I think the lavalier mic will work fine. In fact, you may want to turn it down. Okay, good. Thank you. Ron, Leslie, thank you so much for that great introduction. I didn't know who that guy was after the first paragraph. One of the areas that I've been very interested in throughout my career, but especially in the last several years, has been in the idea of those of us as engineers taking responsibility for technology. There's all kinds of interesting things that we're building. We're providing access to information. We're providing the ability to work, in very unfavorable places, but at the same time, we have to be very careful about what it is we're really doing and understanding, those types of technologies that we're really unleashing on everyone in the world. I think the idea of taking responsibility for technology is even more important now in our post-Macondo world. And I don't think I'm sure, is there anybody who doesn't know the reference to Macondo? Okay, that was that little oil spill that happened in the Gulf of Mexico. Yeah, the people refer to it as the BP oil spill. Since I work in the oil and gas industry, we don't use it as the BP oil spill. We name our oil spills by the area in which they occurred. So, it was the Macondo area, and that was the well that it happened at. And I think there's some lessons that we can take from that I'll talk about, but also there's lots of lessons throughout engineering, and I think we know a number of them, and we have to, as engineers, not only take responsibility, but we need to be able to learn from a lot of those lessons. Let me just give you a little thing more on, in oil and gas, we do this thing called a safety minute. It's a very safety-oriented culture, although you may not think of it as that when you think of some of the problems that happen. But let me talk about some basic technology. How many of you are carrying a penknife or something in your pocket or purse? Yeah, several of you. Well, you want to be careful with that. And that was one of the things that Transocean, who was the drilling contractor, managing technology that was drilling in 10,000 feet of water, managing technology and that's not the deepest place they drill. They have to worry about knives in their process. Their safety says no knives are allowed on rigs. Now we're drilling in these interesting areas, but you can't carry a knife on a rig, so they feel we can't be responsible for that type of technology. When you look at what happened, there's one of the shots just before it sunk. Although I was not on any of the direct committees, I was on several of the research panels where we looked at this. So I've looked at all of the information that became available. I can tell you chapter and verse about a lot of the issues that occurred on Macondo and where responsibility wasn't taken. But one of the key things that I always come back to is that personal responsibility that people have to take as engineers and managers. And this was one of the things, I don't know if some of you may have not read some of these, was one of the more dramatic ones. In fact, Mike Williams, who I've met a number of times and knew him before this accident happened, he was the chief electrical technician on the Deepwater Horizon, which was the rig that went down. It's a very interesting issue. He was interviewed on CNN, he was interviewed on NPR, and he kept telling the same story, as the fact that they're in the life raft, the very last life raft, and it was at a 45-degree angle to the water. There's a painter line that was tied off to the bottom. Now these guys are right about there when this is going on. And they didn't have the technology to cut the painter line. They were looking at the fact, do we swim? What do we do? And swimming really wasn't an option because things were starting to fall off the rig at this time. What happened was there were some fishermen who had been out in the area and were part of the rescue groups that were rescuing people. One of the fishing boats came over, got close enough, and they threw him a knife so we could cut the painter. That's how he got out of there. So when you start looking at technology, it goes all the way down to pocket knives. Where should we as members of the IEEE look at, getting the responsibility? Where do we want to look at what are those areas? Well, I'm sure all of you have memorized the IEEE Code of Ethics. Probably have it somewhere. Actually, it was surprising. I've used this a number of times in IEEE meetings, and I've always had one or two people always say, "We've got a code of ethics?" Yeah. So, we do as engineers. How many of you in here are PEs? Yeah. So, if you're a professional engineer, there's there's the ethics that we've got to use as engineers. As when we put together the CSDP, the Certified Software Development Professionals, there's a big chunk of that's based on engineering ethics and software ethics. So this is a key part of what we have to do as engineers. But where responsibility comes in, I'm going to talk a little bit about number one. Accept responsibility in making decisions consistent with safety, health, and welfare of the public, and to disclose promptly factors that might endanger the public or the environment. So these are some areas things that we need to be able to do. And it's very important that we look to this. The other one is be honest and realistic in stating claims or estimates based on available data. It's another key area that as engineers, as members of the IEEE, we've got to take responsibility for. And I'll talk a little bit more about that after I talk about number 1. And finally, talk about number 5, improve the understanding of technology. Appropriate application, potential consequences. That's part of what we also need to do as members of the IEEE, as engineers. It's part of our responsibility. That education component is what we need to be doing. So let's talk about number 1. Let's go back to August of 1628 and talk about engineering. So August of 1628, the Vasa, which was the most lavishly appointed, most heavily armed warship ever built, it had a little problem in the fact that it sunk on its maiden cruise. And it sunk because of, let's say, poor engineering, poor design, but there were also a number of other reasons that ring very true to a lot of the things that we face today. Remember in 1628 was really before von Leibniz codified calculus. So they didn't have a whole lot of tools available, but they'd had designs. In fact, they'd built designs of this, and they were building design of it. Their customer, their sponsor, was King Gustavus Adolphus, and the king was off conquering Europe. He was at that point in time leading one of his armies in Poland. And what happened was, as he was sailing through Denmark, one of the groups in Denmark was telling him that, you know, we're building a ship that's much longer. It's going to be the longest one in the world. So he immediately sent a note back to his designer that says, make the ship longer. Don't do anything else, just make it longer. He's going through Russia at the time and talking to some people there, and somebody said, oh, you know, by the way, someone's putting, you know, we think it's someone in England, it's either the English or the Spanish, that are putting a second level of guns, of cannons, on their ships. So you do that, and Gustavus Adolphus said, wow, yes, sends back a note, put a second level of cannons on. Now you've got this ship that's longer, not very stable. Anyway, now I'm going to put a second level of heavy cannons on this thing. So we usually call that scope creep. Anybody had that with one of your customers? You know, hey, come on, can't you just put one more microprocessor on there? I know there's 3 already on this DSP, but can't you put 4 on? Because it'll be a lot faster with 4. Anybody from TI here? Don't answer that. So the standard stability test was always interesting. They'd take 30 of their largest sailors, and they'd run from side to side on the deck to see what would happen when it tilted back and forth. The first time they ran, it started to tilt very dangerously, so they said, oh, stop, we're not going to test it anymore. We're just going to deliver it to the customer. We'll let the customer test in production. I think we've heard that before, too. And that's what happened. It went out, it caught a gust of wind, tilted over pretty dramatically, kept on sailing, hit the second gust of wind, tilted over to below where the bottom layer of guns were, and everything kind of started flowing in, and it sunk completely. They only killed 50 sailors on that one. You know, with new innovations, lots of new stuff. Oh, one of the other innovations they had, if any of you who may have grown up on the East Coast around Baltimore or Philadelphia, a lot of those cobblestone streets were made out of ballast from the ships that came in. So they ballasted them with these bricks, very nice bricks, very good. You know, they don't roll around a lot. The designer here decided that they were going to have reusable ballast, and they made it in cylinders. Cylinders. Yeah, you can imagine what happened as soon as it started to roll. The ballast just kind of went with it. So it was all in all, it was a real disaster. Also during this, the main designer, who kept saying yes to the king because he knew what would happen if he said no, the main designer died, and his assistant took over, who really didn't understand what was going on and finished it. So, you know, there's some takeaways that I think we can all see, and probably some things we've, you know, seen before in projects we may have done in the last year or 2 years. December 1903, This was the Iroquois Theater in Chicago. And what happened, the Iroquois Theater was an indestructible, up-to-the-minute design. We have solved all the problems possible. Think of the Titanic, unsinkable. This was a theater that would not burn. And what they did was it didn't burn, but it killed 602 people. And it killed more than twice the number of people who were killed in the Great Chicago Fire, which was 32 years earlier than this. What they did was they decided they were going to install this asbestos curtain. And, I think we've learned about asbestos too over the years. They're going to install this asbestos curtain that would come down between the stage and the audience, so that anything that caught fire on the stage, which happened quite regularly. There were quite regularly fires on the stage because the lamps that were used were either gas lamps or carbide. And carbide had a nasty tendency of exploding, much more than even the gas did. So we've got a technology solution. Here's how we're going to do it. Unfortunately, one of the oil-painted backdrops brushed against an arc spotlight, caught on fire. They started lowering the asbestos curtain. Unfortunately, they hadn't tested it quite well, and it got caught on a stage light and hung up, wouldn't come down. And then the crew and cast in the back said, "We're getting out of here." They opened the back doors, and gusts of wind came in and blew the fire right into the audience. So we have technology that will never fail. How many of us have heard that before? I'll go back to the Macondo incident, and here was one of those technologies, the blowout protector, which ultimately failed. The blowout protector was one of those technologies that in the oil and gas industry, that's one of the main sacraments in the industry, is that the blowout protector will always work. And the blowout protectors almost always do work, as long as they're maintained, as long as you don't have problems with them, and as long as you pull them and make changes to them. Well, there were people on board who relied on that blowout protector. Unfortunately, the blowout protector on Macondo had a problem in there's redundant hydraulic systems on this thing. And you flip solenoids, and it trips the hydraulics, and the hydraulics push the shear rams closed. Actually, it's fairly simple, and when it works, they work just fine. Unfortunately, they had a battery that had gone bad on one of the sides, and they didn't quite have all their alarms up to date on the other side. So one of the problems they had was when they finally realized they had to push the button, it failed because the battery was dead, and they knew the battery was dead. This wasn't one of those, "Oh gosh, how could the battery die?" It was, we had that pink bunny down there, how could the battery go? But it did. And unfortunately, it was the same type of issue here, was, it's fail-safe, we're not going to worry about it, it'll never fail. July 1979, the Atlantic Empress and the Aegean Captain, two gigantic supertankers, collided. Now, it's a big ocean. Anybody been in the Navy? If you've been on a ship, you think, it's a big ocean out there. And these two supertankers were the biggest supertankers built at that time. What are the odds they'd collide? And they did. In a rain squall, they collided. At that time, they killed 26 crew members, and they spilled 280,000 tons of crude oil. Anybody remember this? Anybody remember hearing of this? Yeah, because it was kind of out of sight, out of mind. Nobody reported it, nobody talked about it. This was 4.5 times the oil spill of the Valdez, of the Exxon Valdez. 4.5 times. It was one of those things, again, well, I could probably put in that extra electronic system in my airplane to identify when somebody's too close, but geez, these are big planes. No one would ever not see me. No one would run into me. I don't need that extra piece of expensive electronic gear. This was what they were betting on. This is what these folks were betting on, was the fact that, this would never happen. Couldn't even imagine it. It did. July 1981, there were about 1,600 people gathered at the Hyatt Regency atrium in Kansas City to look at a dance competition. So any of you who are structural engineers out there, used to be structural engineers in a previous life, fourth floor walkway collapsed into the second floor, taking actually 3 walkways altogether came down onto the floor, ended up killing 114 people, 216 injuries. And when you went through the process, the investigation, lack of communication was the major problem. And it was lack of communication amongst the engineers, amongst the construction people, and they just forgot to communicate the fact that they were doubling the load on the 4th floor. And they also forgot to communicate that they were changing how they were structurally tying these together. So communication, how many times have, and I go back to, in my experience with hardware and software co-development, which was always the diciest of all things, as the software guys were busily writing the software because somebody on the hardware design team said, "Yep, design's frozen. Don't worry about it. Go write your software. Leave us alone. You software guys bother us. We've got silicon to make." And you get ready to roll it out and realize that, oh, gee, you're right. We did change that bus from a little Indian to a big Indian. Sorry. Communication. I mean, we see that all the time. Here's another interesting. April 1986, Chernobyl. I was at Los Alamos at the time. You can believe this got us interested. I was also traveling back and forth to Europe quite a bit. I was on one of the NATO subcommittees at the time and had a number of friends throughout Europe, and it was a very interesting process when you could no longer drink milk from northern Italy because the radiation was too high in it, when you couldn't do a lot of different things. What happened in Chernobyl, one of the reactors rapidly overheated, led to a meltdown. Over 4,000 people have died from cancer due to the radiation right now. It still has a 17-mile exclusion zone. If you look at the half-life of plutonium, it's about 20,000 years before it'll be cleaned up and you can actually go in again. The problem here was the fact that the people who were running it were solid, politically correct. These were the right people to be working in our nuclear industry. Unfortunately, they had no idea about how this thing worked. But the government said you've got to have reliable people in here, and reliable people don't always mean those pointy-headed PhD physicists. You can't always trust them. So these guys didn't know what to do when the accident happened, and they really caused the meltdown. It could have been stopped, and they didn't do it. One of the other things, when you look at this, the close but no cigar for us, 3 Mile Island. 3 Mile Island was very close. And you go back and look at the incident report, and I know one of the people who went and did the investigation in '79 who was in there looking at what happened. The reactor vessel was cracked on 3 Mile Island. We had days, maybe, before it would have gone through if they hadn't shut it down. If 3 Mile Island had gone, not even as Chernobyl, if it had just been a massive leak, it would have gone right into the Susquehanna River. The Susquehanna River flows right into the largest crab, shrimp, fish-producing area in the U.S. You wouldn't have soft-shell crabs on the Delmarva Peninsula today if that had happened to us. The other thing, too, is the Hanford N reactor. One of the things we did immediately after Chernobyl was shut down the Hanford N reactor. This is the late 70s, early 80s. Jimmy Carter just went out. Reagan's coming in. The evil empire. We're rattling our swords. We're building lots of nukes. Also, as an aside, if you look back over history, the president who initiated and funded the majority of new nuclear weapons systems of new nukes, who was not Ronald Reagan, was not Dwight Eisenhower, wasn't Richard Nixon, it was Jimmy Carter. So, this was the world that we were living in. That the N reactor was exactly the same design as Chernobyl. There was no secondary reactor vessel. It was built as a fast breeder reactor to make plutonium for nukes. That's what the N reactor was for. That's what Chernobyl was really for. Except they decided, well, we'll get some plutonium and we'll get some electricity too. And we'll stick it right here in the middle of this great area. So again, a very bad engineering disaster. Finally, August 2007, the Mississippi River Bridge. Just get out here and get on I-35 and drive north, and you'll eventually come to this bridge. This was found the problem here was the National Transportation Safety Board. The primary cause was undersized gusset plates. The design was wrong. And it wasn't so much the design was probably okay when it was initially built, but they never talked about the fact or accommodated that they were going to put another 2 inches of concrete on the road surface. And concrete on the bridge weighs a lot. Not only that, they were doing a lot of repairs to it. They had some of the lanes closed, so luckily there weren't as many people on it that could have been on it when it came down. But right on the weakest part of the bridge was where they were putting together all of their heavy equipment and all of their cement and all the material they were using. So it was compounded. It came down. There was no way that bridge was going to stay up. Finally, here's another one from October 2009. I'll go back to the maritime industry. Maersk Line, 18 containers overboard. This is a software glitch, and although none of us can, probably all of us at some point in time in this room have written software or are writing software, even if it's only an Excel spreadsheet. How many of you use Excel? All right. This software glitch was in the Excel spreadsheet that Maersk used to load in their containers. And unfortunately, someone did a wrong sort, and they sorted from lightest to heaviest instead of from heaviest to lightest, and put the empty containers on the bottom. Come on, it's Excel, that stuff happens. Luckily, nobody was killed. As we get back to, go back to what we're doing as engineers, we have to be careful of these things. You never know what we're building today that's going to have some type of impact on systems. And then finally, here's another one on control system failure. And this was December 2009. What was interesting is we do a lot of work with programmable logic computers. PLCs are very straightforward. They need to be tested. They're deterministic. They're great for machine control. You think things would be fine. But in this case, what happened was there was a porch right here on this rig, and there were 8 people standing on the porch, and there had the pipe hanging over it. They were actually doing pipeline subsea in the Mediterranean. And the operator was running it, and all of a sudden his screen, it blue screened. How many of us have had a blue screen? What do you do when it blue screens? You recycle the power. No one had ever tested what would happen when that system was under load and you recycled the power on the PLC. It didn't go to a safe state. Well, it thought it was at a safe state. What it went back to was this beginning state where it unlocked everything and went back to its resting position. When it unlocked everything, it dropped the pipe, killed 4 of those workers immediately, and the other 4 were tossed into the sea. So it had never been tested. No one had ever tested it that way. See, again, it was one of the things like, well, who in the world would ever do that? And that responsibility is what's important. So that's the act responsibly. Here's another one: being honest and realistic and stating claims or estimates based on available data. And I think we could talk for hours about this one. But how many of you have ever been in a position with your boss or with a customer, and they said, We need this delivered the end of March. That's not a problem, is it? And your answer was, why, of course not. We can do that. Or your answer was, no, that can't be done. That's an idiot thing. You're obviously a management moron, and I quit. Yeah, that may be the answer, but not all of us do that. And we have to look at the fact, well, we'll cut some corners. If it's a software project, you look at the Gantt chart and you say, we don't need to do that damn testing. Throw the testing out. That's just a waste of time anyway. And we do those things. So those are some things, we've got to be realistic. We've got to be honest in some of these areas. In many cases, their managers get paid to get things out the door. Project managers many times the same way. As engineers, someone's got to stand up and say, we really can't do it that way. It's not going to work. Here's some other opportunities lost when you talk about people that haven't, and this goes back to Macondo. We knew back in June 22nd, 2009, warned that the metal casing for the blower preventer might collapse under pressure. Most of these people who were out there said there were problems. Many of the people who were on the line doing work took that responsibility. The engineers, the technicians said, there's a problem. They knew accidents had damaged different gaskets. The Halliburton, who was one of the subcontractors, said, hey, use the cement the way you're going to use it. It's against our best practices. That's not the right way to do it. Let's see, issued permit when MMS, who's now gone, exercise caution while drilling due to indications of shallow gas and possible water flow. Well, this was an area that we knew was hard to drill. There had been problems here before. Again, everything in there was known, and this was not rocket science as far as wells are concerned. We drill wells in the Gulf of Mexico. We drill wells in the North Sea, where we'll go down several thousand feet, make a right-hand turn somewhere, and go another 15 to 20,000 feet, and hit a spot. So this was just a vertical well. This was not some really hard well to drill. Let's see, here's another one. As they drill the last section below sea level, they need to be casing it. Halliburton said you got to put a special liner or tieback in. BP said, nah, do a single liner. They wanted to save $7 to $10 million. How many billions did it cost? But they were focused on saving that little bit of money. Let's see, they wanted to use 6 centralizers. The idea of centralizers was, when they put cement in, these centralizers hold the casing and the pipe so that you get a good flow of the cement. Best practices said 21. BP said, we'll stick with 6 because we're not getting any more shipped out here and get this damn well done. So again, people many times stood up and took responsibility and said this isn't going to work, and they were overruled. Finally, we saw what happened. The idea of circulating on the bottom, you circulate on the bottom for days and days and days. BP was tired of drilling the well. The management there was tired of drilling the well. They said, get that ship off of there and get that thing buttoned up. We want to put it into production. And so there was an enormous amount of management pressure. In this case, the engineers, the people who were doing the work stood up and said there's a problem. And in almost every case, management overruled it. This shouldn't have happened. This was one of the things that just should not have happened. And it did because they took risks. And I think when you look at risk-taking, how many times have we taken risks doing things, whether on a job, passing an 18-wheeler in a blinding rainstorm and thinking there's nobody coming, and you made it through. You win enough of these things, you think, I can handle that risk. It's not a problem. I can do that. And that's what they were betting on. And unfortunately, there were too many of them, and it didn't work this time. So we talked about the first one, we talked about that. Just a little bit to improve the understanding of technology. And I'm going to close on this. What I'd like to challenge all of us to do is to work with junior engineers, with fresh outs, with people in college, with college students, with high school students and grammar school students in science fairs so that they understand what it is as engineers and what engineers do, and that from a fairly early age we understand what the responsibility is for engineering. I was lucky. My father worked for Bell Labs and for AT&T, and I remember having transistors around the house that were the size of juice cans, and solar cells in the early 1960s, and we were building radios with those things. And I met a lot of engineers and knew a lot of engineers and understood what that culture was like coming out of AT&T and Bell Labs and Western Electric. And I think that's important. There's a lot of students out today, there's a lot of people working today who don't really understand the responsibility we have as engineers. And I just like to challenge all of you to pick that up and to help promote that as part of our discipline. So, and get a chance, get on the web and just read it once. If we have time, any questions? Do we have a few minutes, Leslie? Okay. Any questions? And oh, by the way, this is yet another Transocean rig that was drilling in the Red Sea, and it took a kick, known as a kick, and what the kick did was it sent all the mud coming right up the wellbore, and it was several thousand feet of mud coming up. But the other interesting thing about it is this guy right here, that's hydrogen sulfide. And when you're drilling in a lot of these areas, if you take a kick, you have to abandon that vessel in somewhere around 45 to 90 seconds. Everybody got off in 83 seconds, 120 people off the vessel. So, technology's tough.
We have time for
one question, all right.
My name is Naresh Chand. I would like to add one data. I wish that you had also included Union Carbide plant in Bhopal, India, as one of the examples.
Yes.
A question to you. Today, engineers are suffering for doing the things right. You mentioned about AT&T Bell Labs, your father worked, I worked there, and we did the right thing. We developed the optical communication system, made the world totally a global village, truly global village, and engineers are suffering today. So engineers' problem today is that they dig their own graves by doing the things right. Any comment?
Well, I'd actually had a slide on Bhopal and decided not to use that when it was a little bit too gruesome. And I think, and again, the concept of engineers doing things right and what we're doing today, I think it's, I think in many cases we are doing the right things. We just have to be more assertive in what we're doing, and we have to be very careful that what we build is, we've done it responsibly. Okay, one more.
I have an example. People don't like the Code of Ethics. Many years ago, I tried to introduce the Code of Ethics to the section XCOM. Excuse me. At that time, the Code of Ethics applied to engineers. So we said, let's apply the Code of Ethics to all members of IEEE and not just engineers, and now it does apply to all. So I introduced the motion at the Executive Committee that we introduce the Code of Ethics and we support and endorse it. Well, I asked for a roll call vote. So we split the Executive Committee down the middle, 7 for, 7 against, and 1 abstention. I want to tell you, the people that were for supporting the Code of Ethics were engineers. The ones that did not support the Code of Ethics, voted against it, were academics and managers. And another thing, if you do something, they don't say you get the most oil, the squeaky wheel not gets replaced.
Yeah.
And Roger Beaujolais was an example of what really happened when trying to support the Code of Ethics to do something right.
Yeah. Well, and again, that goes back to a lot of what happened on the BP. The engineers took responsibility, the technicians took responsibility, the managers didn't. So it was there were different drivers. I think the code of ethics needs to apply to all of us in IEEE. I'll try not to fall off the stairs. Ron?
That would be a tough way to
Yeah.
end the presentation. Don, I have a small gift for you, just as a thank you to you.
Thank you very
I
much.
really appreciate your presentation.
Thank you.